So, we now want to sort of state the problem statement and say, is there something that we can do more than this? And now you may wonder, why are we asking such a question? The question is comes from the following observation. Here is the SNR conditions. This is gamma 1, gamma 2, gamma j. Okay, and each of them has got their own probabilities. Let us take the discrete channel. What are we saying is the transmitted power for each of these? Dot, dot, dot. All of them are transmitted the same power. That's, we didn't change it, we didn't touch the transmit power, right, because all you said was the transmit power, you transmitted at some power, the signal fluctuated because of the channel conditions, noise power remained constant. So, therefore, this is the transmitted power, PS. Now, does it have to be constant? Now, is there any intuition that says, well, you know what, maybe I should do something a little bit differently. So, for example, if the channel condition is not so good, maybe I boost the power, right. So, maybe I can look at a scenario where I do red here and something here. Maybe I try to equalize the channel, where SNR is not so good, I try to do that. Or I may do something little counterintuitive. When the channel is bad, reduce the power, why waste time, why waste power on a bad channel, and transmit it with more power. So, depends on which way you want to do it. So, one thing that we have not yet looked at is the power allocation. So, one option is to keep PS fixed. The other option is can we vary PS? And what should be the criteria? Something should be, it should be somehow linked to the SNR. Can we vary? But the question is then, what is the optimum mapping? That is a very important question. Can we vary the power allocation? Okay. This is an important question because it leads us to the, basically we are building our way towards OFDM. So, this is an important question that arises. So, now what do we say? For each gamma I, I am going to apply a transmit power which is proportional to P of gamma I. I have not defined the function yet, it is P of gamma I, okay. But I have to assign these powers such that, very important condition, summation P of gamma I, F gamma of gamma I is less than or equal to PS. Am I right? I have, on average I have to keep the PS constant. I cannot, I mean I cannot do some allocation which suddenly looks like I have transmitted more than PS. On average I have to do PS. Now, quick sanity check, if I transmit the same power level for all gamma i's, P of gamma I is equal to some constant for all I, then notice that that will come out and you will find that P of gamma I equal to PS for all I. That's a sanity check. So, so what you are saying is, instead of assigning constant power, can I do some differential power allocation? So, this is a very important observation and a question. You know, why do we have to do constant power allocation? Maybe it is better for us to do something or different. So, here is now the problem formulation. The formulation of the capacity. How do we now define formulation of the capacity calculation? Capacity calculation. So, we have a power constraint, okay, it is usually called the average power constraint, and the average power constraint says that we have to allocate power in such a way that the integral 0 to infinity P of gamma F gamma of gamma should be less than or equal to PS, okay, PS, or since we are talking about calling it average power, let us also call it P bar. Okay. So, this can also be rewritten in a very useful way, which is 0 to infinity P of gamma by P bar f gamma of gamma less than or equal to 1. Now let me tell you why this is a preferred model. What are the units of this? It is dimensionless, right. So it is some number. If you did not have any power allocation, what will that be? Equal to 1, because P gamma will be the same as P bar. But now what will it be? If you want to boost it up, it will be 1.1. If you want to reduce the power, it will be 0.8. So basically it is some number in the range 0 to 1, maybe slightly above 1 for some cases, but it is a real number, which is a positive real number, which is in that range. So this is a very useful form for us to visualize and to keep. So the capacity calculation or the capacity formulation is given in this fashion. So I would like to compute the ergodic capacity under the condition of the capacity calculation being the maximum. So I want to maximize the ergodic capacity. So which means it's a maximization problem under the power constraint. Basically it will be the power allocation P of gamma for the different SNRs such that the power constraint is satisfied, average power constraint. Let me just write it down, 0 to infinity P of gamma f gamma of gamma d gamma less than or equal to P, or I am going to write it in the normalized form, this divided by P bar less than or equal to 1. You can take it equal to 1 basically if you want to maximize it. Okay. Now this is the constraint. What am I optimizing? I am optimizing B times integral 0 to infinity logarithm base 2 1 plus, notice I have to write down SNR. This is the SNR without modification, this is what the channel gave you, but you are going to modify it by the following term, which is P gamma by P bar. It is a dimensionless quantity, it either boosts the SNR or reduces it by tampering with the transmit power signal. So this is a very important step. This times basically f gamma of gamma d gamma. Okay. So I just want to pause for a moment just to make sure that you are comfortable with the statement of the problem. I am introducing the flexibility to allocate power based on the SNR. I cannot do it arbitrarily, I must do it subject to a average power constraint. I want to interpret it as a dimensionless quantity which either improves or increases the transmit power or reduces. So basically it is a dimensionless quantity P of gamma by P bar. How does it affect the capacity? It now becomes logarithm of 1 plus gamma P gamma by P bar. This term can either be greater than 1, less than 1, and that will accordingly affect. So under this condition I want to know what is the best that I can achieve. So what am I optimizing over? I am optimizing over all possible power allocations, okay. And this is a detailed derivation that is given to us in Goldsmith, but I would like to just give you the highlights of it. So it is actually framed as a Lagrangian problem, where we say that we would now like to define an objective function. The objective function is J. The variables that I am optimizing over is the power allocation P of gamma. So it is actually a function. This is given by the capacity expression B times 0 to infinity logarithm base 2 1 plus gamma P gamma by P bar f gamma of gamma d gamma, subject to the constraint, the average power constraint minus lambda times integral 0 to infinity P of gamma by P bar f gamma of gamma d gamma, that is it. Okay. So this is the minus 1. So I need to put a bracket around this. Okay. So this is my objective function. So if you could just quickly in the afternoon or whenever you get a chance to look at this, basically we will now differentiate a typical Lagrangian type optimization, differentiate the objective function with respect to the power allocation function, Okay. So, which means that you will have to differentiate the objective function wherever p of gamma is present. What I suggest is take a look at it, but let me just give you the final expression. Logarithm base 2 is difficult for us to differentiate. So, basically we will write log base 2 as natural logarithm of something divided by ln base 2. Okay, so basically we will use that. So it becomes b by ln 2. That's just the, I am taking out the, making it a natural logarithm. So then what we are defined with is you will have to differentiate the integrand. So it will be integral 0 to infinity, the derivative of ln of 1 plus gamma, which will come out to be 1 over gamma p gamma by p bar. Differentiate the argument of the logarithmic function. So you are differentiating with respect to p gamma, so basically it will be gamma by p bar, okay. And the other term comes out to be you differentiate with respect to p of gamma, it comes out to be lambda. Then what you do is basically this times f gamma of gamma. I am basically combining the two terms, f gamma of gamma d gamma equal to 0. Okay, so basically write this, take this p bar to the other side. Okay, so basically it will be integral of p gamma f gamma of gamma d gamma minus p bar. So when I differentiate, I will be left with only this term. Okay, so this integrand is a strictly a positive quantity. It's 1 plus something, right? Logarithm of 1 plus something means it's a positive quantity. So therefore the condition is that if this has to go to 0, then this integrand has to go to be 0. I'm sorry, that's what I said. I took the p bar to the right hand side, right? So it will be so when I differentiate, p bar is treated as a constant. Wait, let me just rewrite that in case this is causing confusion. Minus p bar, right? So when I differentiate with respect to p of gamma, that term goes off, right? That doesn't contribute anything. Okay, so I'm sorry. Common bandwidth, yeah. Let me put it inside. Let me put that inside. Okay. I need to be a little bit careful. So I need to let me keep this. Let me put the b by lambda 2 inside. That's the easiest. That's correct. So let me put the b by lambda 2 inside. Right, is that okay? Okay, so let me just leave you with the thought that this is the solution of the Lagrangian. We are just basically one step away. Let me just write it down and then pick it up from here in the next class. So b times ln 2 gamma by p bar divided by 1 plus gamma p gamma by p bar should be equal to lambda. Okay. So rewrite this equation. Did I make a mistake? No, this is correct. Okay. So 1 plus gamma p gamma by p bar cross multiplying, this comes out to be b by ln 2 gamma by p bar into 1 over lambda, divide throughout by gamma. So then what we get is, this is a very important result, p of gamma divided by p bar, that is my power allocation, that those is actually comes out to be 1 over gamma naught by 1 over gamma, where gamma naught, 1 over gamma naught has been defined as the following: 1 over gamma naught has been defined as b divided by ln 2 p bar lambda. Okay. Now, at the end of the day, B is a constant, bandwidth, ln 2 is a constant, P bar is your average power constraint, that is a constant, lambda is a Lagrangian. So, this is actually a constant, that is why we have written it as this. So, the power allocation is actually given by 1 over gamma naught minus 1 over gamma. Okay. Now, how do we interpret this is the crux of why OFDM was even born. So, basically what we have done so far is we have gotten a channel where there is variations. We now need to find out what is the best I can achieve in terms of ergodic capacity. One way was to allocate equal power, the other way was to allocate differential power with an average power constraint. We went through the formulation as a Lagrangian. We showed that the power allocation, the optimum power allocation should be of the form 1 over gamma naught minus 1 over gamma. Now, what is the interpretation of this and how will it affect us, how will it lead to OFDM? That is the important question which we will pick it up in the next lecture. Thank you.